Welcome to this Unit 19. This will be very short. What I want to do is, first of all, remind you about a couple of things. The fundamental theorem of calculus, which we have seen last time. Then how we really use this fundamental theorem of calculus for definite integrals. That's one of the things. For indefinite integrals, when we just want to have a function, we call an antiderivative a function which has as a derivative the function itself. And we usually write that constant c. So what I want to do is try out something. I watched the MIT Integration Bee, which is a great contest where students compete with each other on the board and are given integrals. And we might actually try out some of these integrals in class. They are usually very, very hard. I chose a few where we have a chance to do them, and I want to quickly go through them. We have already quite a bit of experience, so maybe we can do a couple of them. This one, if you think about it, you have to, first thing you try is to simplify. Can we simplify? So that's one of the things we want to do. And if you are familiar with a 1 minus u square is 1 minus u times 1 plus u, you might just see that we can cancel out things. So simplify. And then we have 1 minus sinus x times 1 plus sinus x over 1 plus sinus x dx. So that cancels away. And so we have 1 minus sinus x dx, which we know how to integrate. We know how to integrate 1, so that's x. And we know how to integrate sinus x, that's cosine x. Minus, the minus cancels, and then plus c. So that's our answer. That's example number 1. By the way, we have just Pi Day today. It's an exciting day. 3/14, that's Pi Day. We always celebrate this at Harvard. And I wrote, just for fun, I wrote you down the pi in a sexagesimal system. So base 60. And also in binary, you can write down pi in any base. We usually write it down in the 10th base. Here are a little bit unusual forms. So that's number 1. Let's continue to number 2. So in this case, this is already factored out. That's usually a good thing if things are factored out. But for integration, it's not such a good thing. It's actually better to multiply out. So this is the integral, and so now I'm just FOIL it out. Right, this is this FOIL. First, outer, inner, last. So we have x to the 8 here. This gives us a x to the 10 minus 2 times 7, which is 14, x to the 4, x to the 6. And then we have a 49x squared. And now we can integrate this. So this is x to the 11 minus 14 over 7 x to the 7 plus 49 third x to the 3. If you want to simplify that a little bit, we can actually write that a little bit simpler. And this cannot be simplified anymore. 49 over 3 x to the 3. And I always just add this c here to indicate that it's an antiderivative. So that's a tough one. I was actually, when I saw this, I was scared, and because we have no idea what to do. But it's actually possible, but we have just to have faith that it simplifies. So simplified. So what we can do is we can just write down, say for example, cotangent x plus tangent x, see what the definitions are. So that's cosine x over sine x plus sine x over cosine x, and then make a common denominator, right? So that's one of the important algebra tricks which we want to do. And so we have a common denominator, sinus x cosine x, and then we get cosine square x plus sine square x. Wow, that's great! Cosine square plus sine square we can simplify. That's 1 over sinus x cosine x. So that's our computation. So when we do that, this integral which we have is actually just the integral sinus x cosine x. And now if you know double angle formulas, you know that, that this is actually just 1/2 sinus 2x, double angle. You might also guess that it's sine square x half, but we just, that's the double angle formula is one of the things. And then so we get cosine 2x minus cosine 2x over 4. And we get plus c. Okay, that's this example. So this looks also scary, but we might want to try a trick. So this is something if you have never seen, it's almost impossible to do. But what we could do is just write 1 over e to the x plus 1. We can write that, wouldn't it be nice if we would have a e to the x here? And then subtract again e to the x over e to the x plus 1. That's a trick, which is actually kind of, that actually tells us this is 1 minus e to the x plus 1. And now you have to see a second thing, so that's already tough. It's getting tougher. I chose the easiest one at the beginning, and it's getting tougher and tougher. Here, this is no problem to integrate, but here you have to kind of have an idea. And actually, if you have something over, the log is always a good thing. So if we integrate 1, so if you have to integrate that, so this is this, integrate that, that's no problem, x. And here we have just to maybe try with log e to the x plus 1. We learn the technique of substitution, which will justify this. But when we do that, that actually gives us by the chain rule the right answer here. And so plus c. So that's a trick here. Which actually becomes a method, the partial fraction. And this will become, this is also a kind of, this we will see a method to deal with this, the method of substitution. For now, that's definitely too hard. The other one, let's look at. Okay, finally we have number 6. And number 6 was the integral log 1 plus x over 1 minus x. That looks tough. A first step we can do is use the log rule. So we have log of AB, or A over B. This is log A minus log B. So if we are using this rule, things doesn't look anymore as scary. 1 plus x dx, and then plus the integral log 1 minus x dx. And now we have to know the integral of the log. That's something we have not done. There will be a method to actually derive this. But if we have the integral of log x dx, we would try just to multiply it with x. So we try. We have not much choice now. We don't have the method yet to do that. This will be called the method of parts, integration by parts later in the course. But just we try now just log x and see what happens. When we take x times log x and we differentiate that, we get really the log x here, but we get the second term because of the product rule. The second term is 1. So we just have to get rid of that term. And we get rid of it with x. So that's the formula for the log. It's actually something you want to know maybe by heart, because this often appears that we have to integrate the log. Differentiating the log is no problem, that it gives us 1 over x, but integrating the log is a little bit tougher. So now in this case, now we know what we have to do. It's just actually we take this formula here, it's 1 plus x. We don't care about the 1 because this doesn't matter. When we use the product rule, you can double check here, minus 1 plus x. That's the first part, that's the integral to this. And then, actually this is minus, very important, I made a mistake here. Minus, so, and then minus, so let me just make it, so it's clear that we made a, then this is the first part, and the second part is just 1 minus x log 1 minus x minus 1 minus x. But we have to be a little bit careful here. If we take the derivative of this in each case, when we take the product rule, every time we get the minus 1 by the chain rule. So this minus 1 becomes actually a plus 1 now. So now we are correct. Now we have a correct thing, then plus c. So that's this MIT. These are these MIT contest problems. If you look at them, most of them I cannot do. So it's a pretty scary contest, but it's fun to watch. You can see some of them on YouTube. Okay, that's it, and happy Pi Day.